And this is how it looks like. What we have available now for our customers is these physical layer chips. Plus what we have available is an Ethernet switch. So this is basically a 5-port switch. And we have partnered, so here we have licensed Broadcom standards. Here, from the company TTTech, we have licensed IP also for deterministic Ethernet. And that is what that is, I'll tell you in a few slides. But in principle, what you can do is with those two chips, you have two Lego blocks. Why did we do that partitioning and not up-integrate all in one chip at the moment? Because at the moment we have no clue how the network topology of the various car makers is going to look like. Yeah? Some of the car makers say, we have one Ethernet branch with let's say 6, 7, 8 of those nodes, and each of those nodes is going as a one-point connection to a radar system. Then the others say, no, that doesn't make sense. Yeah, we have only two at one switch, and we are done. So basically what we had long considerations in how do we do the partitioning to have the best entry into the market in such an emerging market. So what we do is we have single port physical layers. We have, of course, these two glued in one chip, dual port, but then we have a 5-port switch, and this is basically connected either to a host controller, so if you only have that lower part of the story, or of course you can extend to have them more and concatenate these devices to each other. Yeah? The cool thing is here, these physical layers have also the low power management, low power capabilities. We have stolen that from our partial networking CAN transceivers, and what that means is the following. Whenever there is no traffic on the Ethernet bus that is relevant for this control unit, and then this whole thing goes to sleep. If you would do this with existing Broadcom broader reach solutions, you cannot reach that low power levels. And the idea is, of course, to go to microwatts in power consumption as long as the system is not needed. Automatically, that thing goes down. Microcontroller, Mac layer, everything to sleep. If there is a wake-up call, then this device here is listening, but only with the watchdog. So only the watchdog is alive. Yeah, the watchdog has the ear at the rail and says, "Any data package coming? Anything coming? Okay." If something is coming, wake up the whole enchilada here. Hey, everyone, up to work. Let's go. Here, basically, they are all in standby. Worst case, the entire system is waiting for the package to come in, and it's consuming in the range of 1 watt. So this is here a factor of 10,000 at least that you have in power consumption reduction. Yeah, and that's of course massive. Yeah. With some of the sleep modes, low power standards that we see in the industry, you can go down to 2 milliwatts. But here is another order of magnitude, at least in between. This is what we, of course, want to achieve. This is our value proposition into the market, to go out to the car makers and say, you want to have green cars? Take our silicon, you are there. Yeah? And that's the type of know-how that we brought into the, in principle, existing ideas of broader reach to via Ethernet. For that switch, you have always this discussion on, there is certain applications that need some sort of data streaming, that need some sort of data supply, but that's not time critical. Other things, like, and there's FlexRay at the moment needed, are highly time critical for all these X-by-wire applications. So if you do brake-by-wire, steer-by-wire, fly-by-wire, the last thing that you need is that your machine says, I heard your signal, but now I'm doing a 1 second wait state, I brake in 1 second. Yeah, this is of course not what you can use for driving robots. So there is a mix of synchronous traffic. If an action comes, that system has to react. And there is standard Ethernet traffic where you say, just make sure that enough data is constantly running into my buffer of a multimedia streaming, and then I work out of that buffer, that's all fine. So there is very different classes of Ethernet traffic on the network. If everything would be highly synchronous, you would have an enormous overhead to manage and your data rate would go down. Doesn't make sense. If everything would be super sloppy, then your system is totally unpredictable because it depends on the system load, on the bus load, what really is reaching which application. Yeah? And from that, you have the various standards, the low criticality, the normal 8211.3 IEEE standard, streaming standards where you don't want to have interruptions while you're doing video streaming, of course. For an email, it's totally uncritical whether that's coming in, when that's coming in, or if it's coming in jobs. Then you have real-time controls, and then you have things that must not go wrong. So brake-by-wire must not go wrong. Also on an Airbus A380, fly-by-wire must not go wrong. Otherwise, I have an issue coming home tomorrow. So that's basically what we have. We have licensed this IP from the company TTTech that had normal Ethernet switches already in the market for time-triggered Ethernet, so time-triggered technologies is TTTech, yeah, and they are a daughter company partially owned by Audi. And we joined forces there, we licensed that IP and then basically hardened that automotive-wise. What is that all used for? And where is Ethernet already in the market? Well, some of the car makers, I think BMW was the first who introduced a computer Ethernet switch into cars in 2007. That had nothing to do with the story that I just told you, but that had a totally different reason. In the manufacturing side, they could not manage to get the software into the cars fast enough. So if you try to put a DVD into a navigation system, and the navigation system then at the end of the assembly belt has via the CAN bus to distribute all that data, that takes you hours, yeah? So the cars could not leave the assembly belt quick enough. So what BMW did is they introduced several years ago an Ethernet port where they said, okay, here we are plugging the computers of the manufacturing side, doing the software downloading quick enough, download 2 GB and off we go. In the meantime, that is 100 million lines of code that a modern car has. So just to give you a figure, I think that's a jet fighter has in the range of 5 million lines of code, just to give you a bit of a difference there. Order of magnitude. So high data rate download for software flashing in manufacturing is a huge issue. But for that, of course, you can take standard consumer electronics. You never have minus 40 degrees in a manufacturing site when you want to do software loading, nor have you 150 degrees. So it is a pretty straight setting. It is used once or twice every year, maximum, and under very stable conditions. So, and you don't have an issue with the wiring harness because you have only a point-to-point connection to the main unit of the system. Yeah. So here, the standard computer Ethernet broader reach or 100 base T is used consumer-grade electronics. And now what is coming is what I had told you earlier. Suddenly, you have all these systems, up to 15 cameras per car, up to 10 radar systems per car. And the issue that you see in there is each of those systems is providing loads of data, 10 to 20 megabit per second. And okay, you would say, great, Lars, fantastic, let's reduce that data, let's pre-process that data at the camera and then only send a few bits and pieces out. That does not work if you want to have advanced sensor fusion. So if you want to make sure that all data from around the car is reaching that brain, that gray box in the middle that I had shown you on one of the prior slides, then you need to make sure that most of that data directly goes to that big sensor fusion unit. Because that thing needs to have the best environmental information ever. Same is valid for the car-to-car communication. There's high data downstream in the telematics. LTE advanced even goes theoretically up to 300 megabit per second. So there is loads of data going into that sensor fusion unit and are distributed around the car. So you have a lot of these point-to-fusion unit Ethernet connections in the network. And they are driven, of course, by systems like the adaptive cruise control, as of today, radar systems, and the surrounding. On top of that, what we see now, of course, is more and more the car makers are changing the topology of their networks. Whereas prior was a pretty much spaghetti code type of thing. You see now very well structured subdomains for these various branches, IP branches, and this is looking like a computer network more and more, simply because it's getting more complex, simply because you need to separate these domains from each other very clearly to make sure if someone hacks into one part of that network, the rest is not affected. You have firewalling in between So all the issues of modern computer industry, you see now, of course, coming back here again. Plus, of course, you also want to have higher bandwidth for other systems. This is how a modern car network in the next 5 years will look like. So what I forecast from an Equus HKMC car, or from a 7 Series BMW, 5 Series BMW, Audi A8, Mercedes S-Class, and so on. You have one branch, head unit, infotainment part, rear seat entertainment, all connected via one control head unit, but in principle separated from the rest. And here you have the various Ethernet trees, yeah? Point-to-point connections, or even switches going down. Then again, this tree construction here to the body domain, to the main controller. One branch down, driver assistance systems, radar. This here, of course, would fan out into the various radar systems, the various camera systems, and so on. So you will get these type of tree structures in the car network, enabled, of course, via these physical layers that we have, and the switches in between, where you can construct all of these sub-branches. Yeah? And then, of course, you have probably also these remaining flex-ray branches in the car for all sorts of actuators. So the X-by-wire applications, where the 10 megabit are still sufficient. So what I meant prior is this type of architecture we are seeing in today's cars. This is how it's going to look like in future, and you have complete different know-hows in the car makers. Because what you see here is, it's for an IT specialist, this is the most boring picture ever. Unfortunately, or fortunately, the car making industry is of course led by managers that are very often coming from a very strong mechanical engineering domain. So where 20 years ago metal bending and welding were the innovations in the automotive industry, yeah, then somehow these mechanics had been replaced by electronics in the car itself, and now suddenly the car opens up to the outer world. Yeah, but the skills of the managers, at least, the engineers maybe have followed, but the skills of the managers have not followed quickly enough. So there's a big change in the industry, and now these poor guys also have to deal with the issue that there is crazy young hackers out there that even try to screw these systems, and they are, let's say, furthest away from of course, their old home turf. So what we will see is, of course, the car makers are big time gearing up their IT expertise, hacking expertise, networking expertise. Yeah, and this is, of course, for us, it's fantastic. Yeah, security know-how in the company, networking know-how in the company, interfacing know-how in the company. Hooray! We hope that, and of course, microcontroller know-how in the company going forward. We hope, of course, to be the big leading partners for all these guys in future. So. Okay, yeah, so that's basically the simple NXT automotive interfacing story. If you have further questions, of course, I'm happy to answer all of that. And other than that, of course, I'm also looking forward to separate interviews if you like to have us in there. Thank you.